So I think we stop here. Okay. Okay, so today we will continue with this track and talk about this. The first one is the RMS prop. Okay, so you can see here. What do we see here? What's the difference here from the last time? Can you tell the difference by looking at the algorithm? So here is R equals to R plus G times G. So this is a element-wise multiplication. Right? And here you see what R equals to rho R plus 1 minus rho times G times G. Okay? So it's accumulated square gradient. So we introduce an extra. So here we introduce an extra, right? So this kind of like at the beginning, we don't like that extra parameter. Okay, and at the end, we find, okay, maybe still adding an extra parameter will help. Okay, but eventually we improve. So this is, if you look at all this, at the end, we still improve the performance. Still improve performance. And also at the beginning, our idea is to reduce the hyperparameter. Okay, so this kind of trade-off, whether you want to introduce a hyperparameter or not, it's actually depending. It actually depends on whether your performance has a good improvement or not. Whether you think that having that extra hyperparameter is worthy or not. All right, so here, so we introduce an extra hyperparameter, and then use an exponentially decay average to discard history from the extreme past. Okay. So you can converge rapidly after finding the complex code. So this is different from the ADA grade. Different ADA grade. So it kind of result in a premature and excessive decrease in the learning rate. Okay? That's why here kind of make some revision. So we change the gradient accumulation into an exponentially weighted moving average. So for the gradient, right, gradient calculated a long time ago, you don't want that to have a lot of effect, especially when dealing with neural network, which the case is more complicated. Okay, so you think that okay, in the long time ago, that gradient won't provide much useful information. So that's why when that okay, okay. But now you have to introduce an extra parameter for this case. Right, new hyperparameter. So that controls the dense scale of the moving average. So from this from the development of this algorithm, you can tell that okay, this kind of research is always like this. So you have new idea, you want to reduce something, and later you think, okay, I need to introduce something kind of back and forth, back and forth. Then okay, I have new idea. But at the end, the goal is always the same. That you want the performance to be superior to the previous algorithm, and also you want your cost to be lower. I mean, the cost is not the loss here. I mean, the overall implementation cost, all kinds of costs at the end. Because honestly, what what drives our research? what drives all this research? I think we should have some time to talk about something else from the text materials in the textbook. What drives all this research? Is it the dream? I have a dream. Is it because I have a dream? Wow, wow, you are so. Are you really thinking about that? No. Okay, don't forget. Otherwise, so divine, right? There's a problem I need to solve. It's my destiny. I need to solve this problem. Sounds like that. Okay. If that's the case, then I think you are truly you should be go for election. I think you guys know that in 2 weeks we'll have an election, right? Okay. Unfortunately, you don't. Do you have a Taiwan citizenship? No. Oh, you're not citizen. Okay. Okay. Otherwise, okay. That's not too late. If you join Taiwan citizenship, then you can, yeah, you can be elected. I think how many years later, right? Actually, the answer. So go back to my original question. What drives all this research? The answer is actually the opposite of what you talk about. The answer is money. Okay, in Chinese, I don't know how to translate to English, but in Chinese, like 俗气, right? Not the real, not the real. If you tell somebody else that, okay, I do this just for money, your friends or other people say, oh, you're not, okay, I look down at you, right? 中文就是说看不起你了。But after all, everything is driven by actually money. Most of this, in terms of this research, is driven by money, by business. Okay, do you agree or do you agree about it? Yeah. At the end, every research is driven by even the government provide this kind of funding for your research. It's because they expect someday your research will bring benefit to the country. Maybe not in terms of money, but in other, other uh, in other aspects. But all these aspects can eventually be turned into some money, the economy, right? The economic growth of this country. Okay, and the company spend money on the research because they want to make profit one day. Okay, so now you realize that okay, so research you have a good performance. Some you know that to be honest, our why most of research cannot be applied to the real product. You know why? Do you know why most of the research results cannot be applied to the real product? Even some of research, okay, I show you this is the best. This our algorithm has the best performance, and you'll find, and then you might think, okay, I may be able to find this algorithm in the product, but sometimes you won't find it. They what they implement in the product may be something with the uh, poor, maybe a little bit poor performance, but much lower complexity or cost. Okay? Because they want to make profit. It's different from you, right? You want to make the best product in the world. You don't care about your bankruptcy, right? You can you endure the bankrupt? bankrupt. You have no money, right? Are you okay with that? You're okay with that. You have no money. Okay. Oh, you don't, you're not okay with that. Okay. Okay. So too bad. I thought you were. Yeah. If you really like that, I can give you a full credit for this course. So because too bad. Okay. But in fact, you need to make money. Okay. You need to make profit for the company to survive. Otherwise, you can continue having research. You are making good products. Even if you make the good products, but once your company is bankrupt, you can no longer make good products. Okay, so making profit is the very essential for companies. Okay, so you have to either lower your cost and how many of you use 5G for yourself? How many use 5G? What's the reason for that? Too expensive? 4G is enough, right? And is it because it's too expensive? You want to have a 5G plan, more expensive than 4G plan, right? Okay, so and then if you're talking that, so every people is talking about 5G. We start talking about 6G. We put a lot of research on the 6G resource, and at the end, like customers don't want to use 5G. They already spend a lot of money on research, on the deployment, on the product, and at the end, the customers want to pay for that. So yeah, that's a problem. Eventually, and then the company, company will go bankrupt, and then they can no longer develop the new product, the defense product. Okay. So go back to our original idea. So cost is always an important issue when talking about making products. So here we can talk about all the algorithms that this algorithm works better, much better than that algorithm. But at the end, when you make a product, you have to care about what you have to care about the robustness. You have to care about robustness. You have to care about the scalability, the cost, right? Robustness, not just the performance of the algorithm. The robustness is very important. You have the best performance, right? Okay, you say, okay, my cell phone can have the fastest connection in the world when the network is good. But sometimes the network is really bad, right? You have a very bad, a very good, very bad, very good. Is that which one is better? Very good, very bad, very good, very bad, or not the best, but good enough, but it's very stable. Okay, so that there are very many concerns when talking about the algorithm. Because at the end, you have to implement those algorithms on your product, and you have to sell those products. And eventually, your customer will decide. Customer will decide which product they want to buy, which plan they want to go for. Okay, so I didn't mention a lot about the cost. Okay, for other courses, I sometimes mention the cost. When you guys are graduate students, you have to know about this. Okay, when proposing your algorithm, eventually you talk to business guy or people in industry, they will ask you this question: What's the cost of your algorithm? Is it easy to implement? Is it easy to maintain? Right? All right. So yeah, let's go back to the algorithm itself. So not always the best algorithm will win, will be implemented in the product because maybe too complex, too complicated to be implemented, and in the end you don't make profit out of that. All right, so go back to this issue, right? Introducing an extra parameter may sometimes requires extra cost. So you have to evaluate. If you're making a product, you have to evaluate what's the result of that, what's the cost of that, having that extra parameter. Not, of course, not for this case, but in general, you have to consider about it. All right, so this RMS prop. Of course, then you can combine this with the Nesterov momentum. Okay, so what's the difference? And combine with the Nesterov momentum, what's the difference? Here, right? It's a difference. So otherwise, all others are the same. Okay, so yeah, let me 唠叨两句。That's why some of the people in the industry may complain that in the university that we don't teach the students in the way that in the way as the industry. There's a gap. They usually complain that there's a gap between the university and the industry. I think I believe one of the gap is that because we always pursue the best performance without taking the cost or other issues, implementation issues, or even the design. Apple. Not, of course, they have some breakthrough in some of the technologies, but you may find out people complain that their product may not use the best technology, right? Or they do not provide the best hardware. But they have the better design, better user experience. So it looks better, right? It simply looks better. And use more comfortably. But their performance may not be the best. Yeah, so that's in reality there are a lot of issues. All right. So until now we have introduced a bunch of algorithms. Okay. But in the papers, most of the time you won't see, maybe other than SGD, you probably don't see those algorithms. What you see is mostly most likely ADAM. So ADAM is simply an adaptive moment derived from the phrase adaptive moments, ADAM. So the most popular algorithm is ADAM. So you can see as a combination, right? Combination of RMS prop and momentum. Okay, so that's why we have to introduce all this RMS prop and integrate all this. Okay, so in ADAM, the momentum, let's read this first. Go to the algorithm. Momentum is incorporated directly as an estimate of the first order moment with the exponential weighting of the gradient. So we can add momentum to the rescaled gradient. So this is the first thing. We incorporate the momentum into RMS prop. And secondly, we introduce the correction terms. We'll go back to this later. Okay, let's read the algorithm itself. So here, very similar, right? Very similar. We have the update here. You have seen this before. What is this? The moving average, right? The moving average in RMS prop. So here we add a momentum term here, right? S equals to rho 1 S plus minus rho 1 G. So this is momentum. This is not a momentum, right? This is not momentum because R is like determines the learning rate, right? So in the denominator, it's in denominator. So when you apply the momentum, so here S, okay, so here we need to go through a correction term, and then it's just here. Okay, so the first thing is that we apply the momentum. And you can see this is G, right? G, and this is G times G. Okay? And that's why at the end you have to take the square root. All right, let's go back to read this, right? Momentum is incorporated directly at an estimate of first order moment of the gradient. Okay, so we apply momentum to rescale the gradient. And then secondly, we apply the correction factor. So the bias correction to the estimates of both the first order moment, the new item we introduced, and the second order moments already have this in our prop. Okay, so but in Army's prop we didn't have the correction factor. So here we introduce the correction to both. Okay. So here we have a correction bias in the first moment. A correction term. S is divided by 1 minus rho 1 t, so t is time, right? T is the step. Okay. Right. Similarly, you can correct the bias in the second moment. This right, R divided by 1 minus rho 2 t. Okay, and the rest are the same, right? The delta theta equals to minus epsilon times S divided by square root of R. Okay. So this is Adam. Okay. So you kind of correct the bias, the high bias problem in the Army's problem. And usually it is more robust to the choice of hyperparameters. Okay, but still you have to adjust the hyperparameters like learning rate, and other hyperparameters. Still have to adjust them. So he said that it's a more robust. Okay, here's some suggested step size. But in practice, you have to. It's better that if you always refer to some papers, then it's better that you just start with the values provided by the paper. Okay? So Adam is the most popular one. Okay. So which algorithms should you choose? Yeah, if you are not if you are not working on this area, then probably you will just simply choose Adam or SGD. You still find that some papers use the SGD, the basic one, or Adam. If you don't know which one to choose, we'll Adam. Okay, but that really depends on your personal preference. If you have an idea what's the probability of a particular algorithm, then you can make adjustment. I think that most of us use Adam because the papers use Adam, right? And it's always good to minimize the control factor, or you don't want to change that a lot. You want to change everything, right? You have to keep most of the things are the same. But that doesn't mean that eventually you will make that it is much more superior than other algorithms especially in all scenarios. Maybe in some scenarios, maybe other algorithms will work better. Okay, but at the end, actually, you find that some other algorithms maybe have more effect on your eventual results, such as your like the choice of your initial values, the choice your choice of architecture, not your algorithm. You may find that okay, different algorithms may not have the much difference, but if you change the architecture of a neural network, you can see a large improvement. Okay, so algorithms, yeah, of course, algorithm is important, but maybe compared to other other parts, that is not really so important. Okay, so most algorithms is strongly affected by the choice of initialization. Okay, so initialization is very important. You can try that. You find that sometimes you're lucky and it converges faster. Sometimes you're not lucky, it won't converge at all. Okay, so initial point can determine how quickly learning converges and whether it converges to a point with high or low cost. So it's very easy to understand. Right? You can think that the cost, right? The loss function, just like go to the mountain, Zhongyang, the central mountains in Taiwan. A lot of mountains here, mountain peaks, valleys, peaks and valleys. A very complicated terrain. Very complicated terrain. They can think that it's very important. If you want to go to a particular peak, particular mountain, it's very important that which way, suppose, for example, you are carried by a helicopter and the helicopter will drop you, right? And ask you to go to that mountain. It's very important that where the helicopter drop you, right? You are lucky the helicopters drop you right at the mountain, your goal. And you just need to climb a little bit. If the helicopter drops you in Taipei City and asks you to, or Hsinchu City, right? Or other cities and ask you to go to the Mount Jade, like Yushan, okay? Or I just drop you right next to Mount Jade, or even Fangshan, right? Which one is easier to go there? You start from here or start from somewhere nearby? Okay, so it's very that you can if you using that as right as analogy, you can find that okay, very much easier if you choose a very good initialization. Okay, and also not only that, the initial point can affect the generalization. Also, it's less understandable, right? How it is affected by the initialization. Okay, so initialization is very difficult because we don't have a general understanding of how neural network behave due to the nonlinear, right? The nonlinear behavior, very complicated overall. Loss function, not the loss function itself, but because of composition, right? The loss function is very simple, right? If your mean square error is simply the mean square error of the difference between the output and the label. But when you have to write down the output, it's a composition of all the linear layers, nonlinear layers. Okay. And if it was that some initial point may be beneficial from the viewpoint of optimization, but what really cares is the generalization. I've emphasized this for several times. Okay, but we know one thing for sure. Okay, we need to break when determining the initial values, we need to break the symmetry between different units. So we expect different units to have different functions. Otherwise, we only need one unit. Why do we need two units? Because we expect the different units to focus. For example, you are detecting a human face, detecting a face that we expect different units to tell you different things, right? To focus on different regions, eyes, nose, mouth, or right to understand different things. And so it's important that you have to break the symmetry. You don't want them to work on the same thing. If you have the same initialization, right, that time we say that okay, we can easily exchange two units, right? I still have the same result. So you don't want them to have the same initialization. You have the same initialization, and later they will have the same function. At the end, they will have the same, like everything is the same weight. Okay, so you expect that units should have a different initialization. So you have to break the symmetry. So how do you break the symmetry? You actually can uh, purposely make them orthogonal to each other. Okay? You can orthogonal to each other, like so you can have the basis, right? So what's the first time you learn about orthogonality in your linear algebra, right? So in linear algebra, okay, we say we can have the basis functions. Okay, we can derive the basis function, and even you can use the Gram-Schmidt authorization. Like Gram-Schmidt make it orthogonal. Okay, very good, very good. Okay, if you still remember this, then you are very good at linear algebra. So you can search for a large set of basis functions and apply to use it as initial values for different weights. Okay? So what's the problem here? Maybe that's the reason you hate linear algebra, right? Cost. Right? Not a cost. I mean, for this one, you have to spend a lot of time working on homework, and then you derive the results, make it orthogonal, right? It's an implement cost. You have to make sure that they are orthogonal to each other. And this is a cost. The cost is a problem. Okay? We want to make each unit function at different things. Of course, it's best if they are doing things orthogonal to each other. And maybe it's better, but the cost is high. That's why usually we use a random initialization parameters. So we use a random initialization to randomly hope that eventually you still have the comparable results with the real orthogonal ones by computation and much cheaper. But again, this is idea, right? You don't need everything to be exact. You hope maybe you can be very exact, but with the fewer iterations, right? Fewer iterations, but each iteration you takes more time to, right? Or at the beginning you takes more time. Or compared to maybe I will just spend time much less time here. Also, I may need a few more iterations at the end. Okay, so you can compare which one is faster eventually. So the gain from using the real orthogonal one may not be worthy doing that. Okay, so this for weight, usually we just simply use a random weight. And for bias, So for bias, we just use a constant. Bias constant, just choose one and use the constants. We don't initialize randomly. We just initialize the weights randomly, but for bias, we again, what's the reason for that? I think we mentioned this a little bit for different situations, but a similar idea here. Actually, the weights are more important than the bias. Usually it's more important than bias. Okay, and of course you can make a bias. You can apply randomly or even orthogonal to. But you don't probably put all your efforts, but you don't see that much gain. Okay, so we decide to use random values for weights. And random, talking about randomness, you can look about all the distribution, all kinds of distributions. The most popular one are, of course, you guys know the Gaussian, like uniform distribution. So you can apply Gaussian distribution or uniform distribution. Okay, you can try it, but in fact, that which distribution, using which distribution is maybe not that important compared to the scale. What scales do you allow for the initial values? More important. And the scales, what's the range? If a uniform distribution, what's the range for that? Okay. So why is that? What's the concern of the scales? The range of the values. What's the concerns? What are the concerns? Actually, the keywords I mentioned, the keyword. If you know nothing, you don't know how to explain why your neural network failed. How to explain to your advisor? The keyword, the keyword. Right? It's too large, then you have exploding values, right? Exploding, right? Exploding gradients, right? Exploding gradients, vanishing gradients, right? Yeah, so that's the idea that people that keep coming using those ideas. Right? If you are too large, right, you may easily saturate, right? You may easily saturate your nonlinear functions. Of course, that if you have a large initial weights, okay, you have a lot better symmetry breaking effect. They have much better difference. Okay? But the problem is that if it's too large, then you saturate the units, and you'll get good gradient information. You want the weights to be large enough that so you can provide enough gradient information, right, to guide you to go to which direction that you should go. But if it's too large, you saturate units. So in recurrent neural networks, large weights can also result in chaos. Chaos is a case that it is extremely sensitive to small perturbations of input. So if you change the input slightly, if you change the input of the system slightly, and it shows a big change at the output, and this system is a chaotic system. All right, so in case you want your weights to be large enough, but not too large, to avoid the exploding gradient problem. the keyword is Spalding gradient. So yeah, if you don't know why, and just say, okay, Spalding gradient. Okay, it's Finnish gradient. Okay, not just me. If you read the papers, you'll find that when they explain, they will say, okay, this is great. Yeah, before we understand, we have further understand of neural network, and this maybe one of the best skills you can. Okay, but for my students in my lab, you are forbidden to use this. Okay, so and then of course we have other ways to mitigate this problem, right? Okay, we can use the gradient clipping, right? Gradient clipping can thresholding the values of gradient. Okay. So the same thing, you can cause the activation function to saturate. Okay, so you have to set the range. Of course, you have to try a little bit. You have to try a little bit to see whether they will saturate your nonlinear units. Okay. Okay. So the idea, the overall idea is that the final parameter should be close to the initial parameters when using the stochastic gradient descent. So yeah, you can expect that because they're using iteration, right? Iteration. And with the small step size, usually, and you don't expect that the initial points will be much different from the final values. So you have to choose the initial values carefully. Okay. So one thing people usually do is that for a fully connected layer, fully connected layer with the n inputs and n outputs, then you can do this for normalized initialization. Okay, you can choose this range. You can choose depending how many weights and how many units. Right? Then you may use this. Okay, and initialize random octagonal matrices. Okay, and this too costly. We already mentioned this. Okay, we're chosen scaling of gain factor. Cost 1 year ago. Okay. So once you can set here, you just want to say that if you can set the gain factor correctly, then you do not really have to care about the orthogonality between the different units. I'm going to skip this one just to explain that this because of random walk behavior, you can as a different layers you have different large or small values, and overall it should be fine. So in practice, we have to treat the scale of the weights as a hyperparameter. So you can choose using this. You can choose using this rule of sum m plus n 6 divided by n plus n, or uh, you can use this one or this one, or you can treat the scale of the weights as hyperparameter and try a different value to see which one works better than the other. The reason you have to choose, okay, you say, okay, we already have some guidance here. Why do we need to try different values? Okay. First of all, you may have using the wrong criterion. Another reason, right? We have introduced that, okay, so everything is approximate. Everything is approximate. Remember that even the loss function, we do not use the real loss function. Remember that? We use a surrogate loss function, not the real function we expect at the end, right? So a lot of things are approximate. The algorithms, the optimization algorithm is an iterative algorithm. It's not guaranteed that you will reach the optimal anyway, right? So a lot of issues. So that's why it's complicated. Secondly, the properties in cross initialization may not proceed after learning has begun to proceed. Okay, maybe you can have a good analysis. A good analysis, okay, what it may look like. But remember once we we discuss chapter 6 or what, we have two discussion, right? We have the initial, right? We can look at the points near the optimal point, more like static analysis, or you can go through the whole learning process. It looks like the whole learning process. So it's different when you incorporate. Once you start learning, things is different. Your analysis is different. Okay, so you don't maybe you don't have the same property that you expect at the beginning. Okay. Finally, we don't know how you generalize what's the relationship between the optimization and generalization, right? You know that you have already solved one of the biggest problems in deep learning. You can map the training error and with the generalization error. Concrete relations, you can definitely learn one of the big prizes or like big medals in this area. So we don't have much information. Okay, so you can try it as a hyperparameter, okay? Or use the one I will mention 1 divided by square root of m. But this method has its own drawback. Okay? What's the drawback here? When m is large, and what is m here? You have m inputs. When m is large, that means this value is small, very small. Very small. What problem do we have when the values are small? Vanishing gradient, right? Vanishing gradient. You don't have, you almost have zero, or your units are not activated. Okay, so you can fix this problem. You can fix this problem by using the sparse initialization. So each unit initialized to have exactly k non-zero weights. Okay, so you can keep the total amount input to the units independent from the number of inputs m. Okay, so you purposely made you only activate, you have k non-zero weights, other weights are zero. But they will cause some problems. That means that you have very strong fire. Okay, how do you choose which weights should be non-zero? How do you choose the weights? Which weights should be non-zero? Okay? It kind of has some bias at the beginning, right? Okay, this weight should be non-zero. That weight should not be non-zero. Okay, so this initialization scheme can cause some problems. So if your resource allows, then it's always better to treat the scales as a hyperparameter. Okay? or you can use of course nowadays you can use packages for the initialization, or you can manually search for the best initial skills. So this is different from other hyperparameter search, because here you only need to take look at the few starting points, look at a few initially, okay, how it behaves, maybe. Now, of course, you may argue, okay, long term, and long term, that this parameter may be better than that parameter. Right? In short term, this one is better, but long term, okay. In this case, then you have to run all the experiments, right? All your training to the end. But sometimes you can decide quickly that what's the scale. At least you can exclude some of the cases. Because at the beginning, you don't see that improve at all, then you know it's a problem, right? If you, in the case, if you see this kind, right, it's quite often you see the training like this. Right? You don't go down at all, then you know that's a problem. You can change. Of course, there might be a lot of issues. Simply your programming error or the programming error that sometimes the stupid programming error can happen. You just override you. Okay. So the bias, okay, for in terms of bias, easier, right? You can just say the bias to 0. You say the constant value, 0, so constant value. But sometimes you might your bias to be non-zero, but still constant, still constant. The bias is for an output unit, and you want to set the bias to match the statistics of the output. I want to set the bias to make sure that they match the real average. This is the average of the output. Okay. Pretty much the same, right? Second thing is that you want to avoid causing too much saturation initialization. So try to repeat ourselves, right? Those things you want to you don't want to explode the gradient, you want to banish the gradient. I don't want to saturate things because nonlinear, right? Linear. Whenever nonlinear, that's why this now you start to appreciate the linear stuff, linear system. That's why we usually deal with linear systems. We want to avoid the nonlinear systems. Also, we know that nonlinear systems will give us some extra benefit, but it's more difficult to develop, more difficult to implement, more difficult, especially more difficult to analyze. Right? You see the problem here. Okay, you can implement that, you can train that, but you cannot analyze it. It's more difficult to analyze it. And this is a big issue. It's really a big issue because a lot of things back to the, you know, uh, in someone in industry, you want some guarantee. So it's different from writing papers, right? Writing a paper, okay, I can claim how good and how good the proposed algorithm is. But in industry, when you're making the products, your customer will buy your product and they will complain, right? They will sue you. They not just call the customer service, but at the end they may sue you because what you claim you cannot guarantee, right? You cannot guarantee what you claim. So how can we guarantee when developing algorithm? How can we make sure? How can guarantee this? Sometimes, a lot of time, you have to rely on your analysis, mathematical analysis, to provide you some guidance to show you, okay, this is guaranteed. Because running the simulation is cannot provide you a guarantee. How many simulations can you run? How many cases can you run for your life? Why? people can always challenge you. How about another case? How about another case? You cannot exhaustively run all the cases. But by using some mathematical theory that you can at least provide some performance guarantee. Okay, but for neural network deep learning, how can you get this kind of performance guarantee? Okay, this is also what people are scared about. Okay, you say your system has a good performance. How do you guarantee that one day, okay, for example, we have a robot, right? For example, this robot performs very good. How do you guarantee that one day it won't turn to a killing machine? You have watched a lot of movies. Even in the superhero movies, right? They can easily turn like the robot into a killing machine, purposely or spontaneously, right? By itself. How do you make sure that you write a program at the end, it won't one day realize, okay, the best way to save the earth is to kill all humans? Have you watched this kind of movie? You realize the best way to save the earth or save the human being is to kill most of the human human being, right? So that okay, then we solve the problem. We have too many people, not enough food, people are greedy. So the best way is that we just keep the some people, right? And it's scary, right? That how do you guarantee that this robots will one day turn into? I think that's a problem in AI in general AI that people argue about it. Right? If you cannot guarantee the performance, the things you develop, right? Sometimes it can be scary. Not just the bad performance. You won't just get the call of customer service. Right? You won't just get right a lawsuit. Instead, you're just it's about our future. Do you agree with that? Understand what I'm talking about? Understand the what people are feel, they feel uncomfortable about the fence in AI. Yeah. So in the past, when I started the machine learning or deep learning or other courses, uh, at the beginning we didn't have this large group. So now we still don't have a large group in the classroom, but we still have almost 100 people. Right at the beginning, we have a very small group of students, so we can have the debate about all those kind of issues. And we don't have a lot of students, so we can have, at the end of the semester we can have a debate. So how do you make sure? Do you think the AI will be better? Is it better? Will that be better if we have AI or not? Okay, so you can argue that okay, we need the AI to improve our life. So the other group will say, okay, we probably don't want AI to control our life eventually. So in the past we have this kind of debate. Yeah, but anyway, it's always a good to think about all these kind of issues. Okay, okay, so why did I go? Why did I talk about that? Okay, yeah, I think because we have some extra time, it's good to in this course since we are talking about artificial intelligence in general, right? Some of the key technology in AI, eventually we have to touch that issues. Okay, and the concern is particularly when you look at some of machine learning algorithms. Actually, some of machine learning algorithms are actually guaranteed because in general, most of machine learning algorithms are have strong mathematical foundation. But deep learning, because of the nonlinearity property, so nonlinearity, so a lot of analysis cannot be formed. Okay, so that's the issue. Okay, so here we want to choose a bias to avoid too much situation, right? Okay, say the value hidden value to 0.1 and 0 to avoid saturating the unit at the beginning. Right, so the third problem is a unit controls whether our units are able to participate in a function. So the third scenario that you probably don't want to set the bias 0, that if a unit, you want to activate this unit. Okay, because this unit control that. So if it is not activated at the beginning, you won't be activated at all, right? You won't be activated, and the other units will not be activated at the beginning, and eventually may be a problem. So, for example, like in the LSTM model, so next week we'll talk about LSTM. Set a bias to 1 for the gate of the LSTM model to make sure that this at the beginning can be activated. And another hyperparameter is usually the variance. They can most of the scenarios you can set the variance to 1 without causing too much problem. All right, so that's some methods. But we have some advanced methods, like you can initialize the model parameters using machine learning. What do we mean? We have several methods. First one is that you can use a unsupervised model trained on the same input. You can use a supervised model, do some training or use some supervised model, and then use the values you get as the initial values. Okay, the supervised learning first, and then go to unsupervised learning method first, and then supervised learning. Or you can rely on other supervised learning on a related task. Not the same, but the related task. So usually this related task is easier to train, easier to set the parameters, easier to train. Okay, or the model that your classmates or your roommate or lab mate have already trained. You can say, okay, let me borrow your initial the ways that you have already trained and use it as my initial. Okay, so this kind of like a pre-training, initialize your model parameter using other supervised training on the related test. And actually, you don't need a related test. You can also use on the training on an unrelated task. It will help. You just need other people. You just need to get other people's weight. They usually have a better result. Okay, so you can, of course, you can start with the random, or you can start with the randomly looking at your classmates or their neighbors. Okay, both are random. Okay, so you can think that this may be because that training that there's something universal. Maybe there's something universal or related at underlying phenomena maybe related. So using the ways that is already trained will help. Okay. Yeah, it's kind of pre-training. This also a kind of pre-training. Pre-training. The same way. Okay. So the overall idea is I set a parameter to have the right scale, okay, and set different units to compute different functions. So this is the idea. The basic idea is this: make make sure they will they will compute different functions at the starting right at the beginning, and they make sure they have the right scale. They won't saturate. Right. So this the initialization. Yeah, that's maybe yeah, because I need to upload the. Let's take a break, okay? Here, so I can download the slides. 255.